Greetings, chemistry students. Today we're going to be going back to the PowerPoint on percent composition and empirical formulas, and we're going to be looking at something called empirical formula, which is a way to kind of reverse percent composition problems and work backwards to find what the chemical formula is. Now, the empirical formula is defined as simply being the simplest ratio of elements in a compound. I'll explain more about that in a few minutes once we work through a couple of examples. But the process for calculating empirical formula is first you assume that you have 100 grams of the compound. And we're going to take a look at a sample problem where we have a compound that is 40.05% sulfur and 59.95% oxygen. So that's its percent composition, or its percent by mass. So if we assume that we have 100 grams of the compound, then these percents essentially become grams. So instead of it being 40.05% sulfur and 59.95% oxygen, if we have 100 grams of this stuff, then we have that many grams of each. And then some of you might be able to guess where this is going next. The third step is to convert these grams that we have now come up with into moles. So we're going to take our grams of sulfur and turn them into moles of sulfur, where 1 mole is 32.07 grams, because that's the number off the periodic table. So we take 40.05 times 1 over 32.07, and we get 1.25 moles. And then we do the same thing with the oxygen. Its mass on the periodic table is 16 grams per mole. So do a little bit of quick math and we get 3.75 moles. So on a mole ratio, and moles are analogous to particles, they're directly proportional to particles based on Avogadro's number, we have a 1.25 to 3.75 ratio, which would mean that essentially we have a chemical formula that is C1.25, not C. I mean, we have a chemical formula that's something like S1.25 O3.75. And that's no good because we can't have decimals as coefficients. So we need to get these into whole numbers. The way we do that is with item number 4, where we're going to divide everything by whichever number is the smallest. So the smallest number we have out of 1.25 and 3.75 is 1.25. So we divide everything by 1.25 and we get 1 and 3. So that means that our new empirical formula is S1O3, or sulfur trioxide. Now, I'll also show you that if you don't end up with whole numbers, then we would multiply to get whole numbers. Because sometimes when you do this last step, you'll get something that ends in a 0.25 or a 0.33 or a 0.50 or a 0.66 or a 0.75. So if you ended up with one of these decimals after you do this step, not before, not here, but after you've divided by the smallest number of moles so that you get one of these down to 1, essentially, because this is guaranteed to get us to at least one whole number, because when you divide a number by itself, you get a whole number, 1. After you do that step, if you need to, you could multiply everything by 4, by 3, by 2, by 3, or by 4 to get rid of those decimals. These are some common ones. That's a fourth, a third, a half, 2/3, or 3/4. So if you get something in those ballparks, you can do that. If this had come out to be 2.99, we would just round that off to 3 to get us whole numbers. Our empirical formula is SO3. And if we look at that, that's the example that I've got right here. If you want to go back through the PowerPoint, you can work yourself through that as many times as you want. So let's take a look at another example. What is the empirical formula of a compound that's 48.64% carbon, 8.16% hydrogen, and 43.20% oxygen? If you want, you can try this on your own real quick. So you can pause the video. And now we're going to look at how to actually solve that problem. So we have our percents, and the first step is to make these percents magically turn into grams. Then we need to convert these grams into moles using the numbers off the periodic table. And for the carbon, we get 4.05. For the hydrogen, we get 8.10. And for the oxygen, I'm getting 2.70. So at this point, we would divide everything by the smallest number of moles, which is 2.70. This comes out to be 1.5. And this comes out to be 3. So this is a case where we need to take everything and multiply it by 3, and we get 1.5. I'm sorry, not by 3. We multiply everything by 2. Sorry about that. And we get 1.5 times 2 is 3. 3 times 2 is 6, and 1 times 2 is 2. So our empirical formula is C3H6O2. All right. Now, there is a problem with empirical formulas. And I said, empirical formula, if we remember back from the initial bullet point of the slideshow for today, it says empirical formula is the simplest ratio of elements in a compound. And the reason this creates a problem is, let's consider these 3 compounds right here. CH2O, C3H6O3, and C6H12O6. They all have the same ratio of carbons to hydrogens to oxygens. It's a 1 to 2 to 1 ratio. So the empirical formula is CH2O. It's the simplest ratio. The problem is these 3 compounds are all unique and distinct and very different from each other. C6H12O6, you know that as glucose. C3H6O3 is vinegar. And CH2O is formaldehyde, which is an embalming fluid. And the reason this is the empirical formula, the other thing about this is all 3 of these compounds would have the same percent composition. So if we started with the percent by mass of glucose, when we work to calculate the empirical formula, we're going to come up with CH2O. So we need another data point to get us the actual chemical formula we're looking for, and that is the molecular formula. So if you have the empirical formula and the experimentally determined molar mass of the compound, you could calculate the actual molecular formula of the compound. And the way you do that is you divide the actual molar mass by the molar mass of your empirical formula, multiply the subscripts by that number. Now that seems complicated, and I'll explain what I mean. It's really not that hard. So maleic acid has this percent composition, and its molar mass is 116.1 grams per mole. What's the molecular formula? Well, the first step is we're going to calculate this just like an empirical formula problem. So we're going to take our grams and turn them into moles, because we're going to pretend these percents are grams. grams, grams, and grams. 1 mole is 1.008 grams, and 1 mole is 16 grams. So for the first one, 41.39 or 12.01, we get 3.45 moles. We get 3.44 moles. And we get 3.45 moles, which is kind of interesting. We divide everything by the smallest number, 3.44. You can kind of see where this is going. We're going to get 1, 1, and 1, essentially, when you do this math. So the empirical formula is just CHO. Now, if we calculate the molar mass of CHO, it comes out to be 29.02, which is not the molar mass we were given in the problem, which is 116.1. So what we do is essentially this molar mass is some multiple of 29.02. So we take 116.1 divided by 29.02, and we get 4. So CHO is our empirical formula, but the molecular formula is going to be 4 times as heavy. So it's going to be C4H4O4, which is our molecular formula. C4H4O4. Right? So I've got one more for you to practice. So pause this video right now and see if you can work this problem out. All right, so let's check and see how you did. So you convert your grams into moles. You divide by the smallest number of moles, and you come up with a 4 to 4 to 1 to 1 ratio, which gives you an empirical formula of C4H4NO. If you add up the mass of 4 carbons plus 4 hydrogens plus a nitrogen plus an oxygen, you get 82.08. If you divide the molar mass we're given in the problem by 82.08, we get 2, meaning the actual compound is twice as heavy. So the molecular formula is C8H8 into O2. As you will see, occasionally you can actually get a case where the molar mass that you calculate for the empirical formula and the actual molar mass are the same. In that case, if that comes up, for instance, like it will on your assignment for today, the empirical and molecular formulas are the same.